This is more than you ever wanted to know about the Earth's magnetic field. So the Earth generates a magnetic field, and that's the reason why compasses are useful. We are not the only planet that has a magnetic field around it. And the origin of the magnetic field is there are these currents of molten iron that are circulating around in the outer core of the Earth. And as you know, a moving charge, a current, is what generates a magnetic field. So the Earth generates a magnetic field, which you can basically approximate by saying it's just a dipole. And the idea is that the Earth is a giant dipole like this, and therefore it puts out a magnetic field. And again, the kind of surprising thing is that the Earth's geographic north pole is really a magnetic south pole, which is why it attracts the north-seeking pole of a compass. So the field lines kind of go like this. Now, the thing about the Earth's magnetic field, it is uniform, over, say, the size of a classroom or something like that. But as you can see, it's not exactly uniform over the surface of the Earth because it's a dipole field. It doesn't have spherical symmetry or anything like that. So in general, we tend to specify the actual observation of the magnetic field relative to kind of what we expect. So we would kind of expect the Earth's magnetic field to always be completely horizontal, meaning completely parallel to the surface of the Earth. And we'd expect the field to always point directly north towards the geographic north pole of the Earth. Both of these don't really happen. So we want to specify the magnetic field. And in general, to specify a three-dimensional vector, you can either do it in terms of three components, or you can do it in terms of a magnitude and two angles. So the magnitude is just called the intensity of the field, and the two angles are the inclination and the declination. The inclination is, like I said, how much is the field inclined to the horizontal. So you can see that near the North Pole, you actually have the field that kind of points downwards towards the Earth. Near the South Pole, it kind of points upwards away from the Earth. And only at the equator is the field actually horizontal, actually parallel to the surface of the Earth. So you've got this inclination, how much it points up or down, instead of just being parallel to the surface of the Earth, which is kind of what we imagine it should be naively. The other thing we talk about is something called the declination. And the idea is that we expect that the north pole of a compass will always point directly at the geographic north pole of the Earth. This is actually not true because the geographic north pole of the Earth isn't even the exact spot for the magnetic south pole of the Earth. So that discrepancy is called the declination, which is to say, how much is my compass going to read off? How many degrees off is the magnetic north going to read compared to the geographic north? So here's how the declination has changed over the years. This is, model simulation over the centuries. And you can see that it does really vary over the course of years, decades, or centuries. Now, the huge changes in declination right here are where your compass is going to be very far off compared to what the Earth's magnetic pole is. And that's just because that's where the magnetic pole really is. And that's why you're getting this big discrepancy between what the compass reads and kind of what your latitude is on the map. Here is the declination as of 2015. So you can see the big deviances here and here on account of the fact that that's where the magnetic north pole and south pole of the Earth actually really are. That's where you get these big readings where the field is actually a far different direction compared to the direction of a geographic north, according to latitude, longitude lines. Inclination, like I said, is how much the field is kind of pointed up or down, compared to the being parallel to the surface of the Earth. And you get basically what you expect, which is that in the northern hemisphere, the field is mostly pointing into the Earth, so these are negative inclinations. And then in the southern hemisphere, you get a field that mostly points up into the air, so that's a positive declination. So you get basically what you expect with an interesting variation around here in South America. The intensity, so the strength of it, that also varies a bit over time. So this is going from the year 1600 to the year 2100. And you can see that in present day, as it goes over here, you have a big drop in intensity right here around the South Atlantic near Brazil again. So funny things are happening there. And this is the present day or 2015 measurement. So what's going on? Well, you have this spot of extreme magnetic field weakness around like southern Brazil, Argentina, Paraguay. And then there's kind of a counterpart on the opposite side of the Earth where you have a field of anomalously high strength over here over Siberia. So what exactly is going on that we get such a big variation here and here? And the answer is that the magnetic field of the Earth can be thought of as the magnetic field of a dipole. It's actually a perfectly good approximation. But if you actually take the measurements off of this, the center of the magnetic dipole moment of the Earth is not actually at the center of the Earth. It's actually offset a little bit. So the dipole that's representing what causes the magnetic field from the Earth is actually a little bit off to the side from the actual geographic center of the Earth. And as a result of that, the part that it's a little further away, that's the South Atlantic, South American field anomaly, South Atlantic anomaly. And then on the opposite side here, the field is a little extra stronger because the dipole is actually a little closer to that. That's over in Siberia. And like I said, these are all time-dependent things. We think of the magnetic field of the Earth as being just like a field, and it doesn't ever change direction or anything like that. It just kind of is constant, and it's just not true. So even over the course of a decade, or even over the course of a year, the poles are changing. So specifically, if we just looked at like the magnetic South Pole, which is over the Earth's geographic North Pole, here it is in Canada, and it's kind of heading towards Siberia at about 45 kilometers a year. So that's the direction of the shift, as the iron currents in the outer core of the Earth are shifting their directions. So it doesn't actually stay in place, it actually shifts. And here's just a measurement of the change in declination every year. So again, the declination is just how far off is the compass going to be compared to like a latitude, longitude, like north, a geographic north. And so you can see as the North Pole, the magnetic South Pole of the Earth, is wandering towards Siberia. Basically, you just get that the declination measurement of the field at that point just changes very suddenly. And then just the last point I'm going to make, which is how do we know this? We've got these graphs that show the Earth's magnetic field over every possible point on the Earth. Are we really measuring it everywhere? Well, what we actually do is we have measurements from about 100 points over the surface of the Earth. We measure the intensity, declination, and inclination of the field at all these places. And then we just feed it into an analytic solution. So a disappointingly large number of problems in physics are there's some big differential equation that you're trying to solve. You drop in the particulars of the symmetry of the situation, and you just get that the solution is an infinite power series of various functions that involve coefficients. And so then you just take the observations of these 100 or so data points there, drop it into your model to figure out what the coefficients are, and from that you can extrapolate to what the magnetic field of the Earth is at all points on the surface of the Earth.